Welcome back to the digital image processing lecture series. So we are almost there at the end of term 1, and this week we are going to discuss two applications, one on image blending or image compositing and the other one on image compression. And for both these applications we'll be leveraging some of the ideas that we discussed over the last few weeks especially of term 1. Okay. So without wasting any time, let's discuss about one of these applications to start with, which is image blending. Okay, so image blending or image compositing. Okay, so what is image blending? Okay, so I'll take, I will illustrate this with the help of this particular example. Okay, so we have the image of apple, let's call that as image 1 or image A, and we have the image of an orange, which is image B or the second image. Okay. And what I'm going to do is I am going to define a mask. Okay, so this mask is something like this. So inside this white region I want to keep the first image, and outside of this black region I want to keep the second image. Okay, so as simple as this. Okay, so if I going to add these two images such that this white region will be having the image of the apple and the black region will be occupied by the other image, right, the image of orange, I get something like this. So in terms of mathematical expression is nothing but m, which is the mask image, will be multiplied by I1. Okay, so the black region will go, right, the black region will get cut off from this image, and 1 minus m is just the inversion of this. That means this becomes white and the inside region becomes black. So if I multiply such a mask with this, what essentially happens is this inside region will disappear, the outside will remain, and that's what exactly happened. Okay, but this doesn't look good, right? Definitely you are going to see that edge, okay, that boundary. So in image blending literature, this boundary region is typically known as, okay, this boundary region is typically known as seam. Okay, so if you come across image blending papers, they will talk about the seam and all. It's nothing but that boundary, this particular region. Okay, so this particular boundary, sorry for my drawing, I just draw it. So this is the boundary, right? So this boundary region is known as seam. Okay. So that's really evident here, right? I mean that the transition from image A to image B is very, very evident here. So what we can do better? Okay, so this direct blending is not going to work. It's really creating an artifacty look, right? It's not appealing to the eyes. So what we can improve? So one thought process I have in mind is shall I smooth this? So the reason why there is a sudden transition that you're observing it's really striking for your eyes is because there is a sudden transition, right? You go from this black to white in a sudden way. So what shall I do? Shall I do some filtering? Shall I do a Gaussian smoothing of this thing? Okay, the mask. So I do a filtering, a smoothing on the mask, and then shall I use the same expression? So what will happen? Let's see that. Okay, so here what I did is a filter operation on M. Okay, so this guy is filtered. Okay, and then essentially the same equation is kept. So what we are trying to achieve there is, instead of a sudden transition, we are having a smoothed transition. Okay, so then f of m is nothing but a smoothed version of m, and 1 minus f of m is nothing but the inverted smooth version of m, and that's it. The equation remains same, and you see the result difference. Now you don't no more see that sudden changes, right? It's almost smooth, but still it's not really that. You can see a local transient, I think, sort of change, right? Even though that it's not transient, it's local variation, it's evident, right? So can we do something better? Okay, and that is where the concept of pyramids that you learned in the last week helps a lot. Okay, so what is pyramid? Pyramid is actually you are going to smooth the image and then downsample, you further smooth it, you downsample. So basically you are scaling the image, right? You are sort of reducing the image in terms of frequency. And if you have the Laplacian pyramid, basically the subtraction of the smoothed image from the original image, you get more of edges, but again edges also you are viewing it at different scales. So image is actually viewed at different scales, right? So that approach is typically known in literature as something known as multi-scale or multi-resolution approach. Okay, so basically you are reducing the resolution of the image or the scale of the image. Okay, so can we apply the similar concept? Okay, similar concept of not this one. Okay, this is pretty useless, but this concept, can we apply it at different scales? Okay, can we do this sort of masking, smooth masking at different scales and then reconstruct the image back? So that is exactly what we are going to discuss today, and it's quite easy, quite straightforward, but you can see that it's very, very powerful approach. Okay, so we are going to use image pyramid concept that we learned in the last week to come up with a better image blending or better image composting. Okay, so let's discuss that. What is the crux? Before that, let me just briefly review the Laplacian pyramid concept that we discussed in the last class. Okay, so this is what Laplacian pyramid is all about. If you are really not knowing that, just refresh that now. So you have the original image, you pass it through a smoothing filter, or a Gaussian filter for example, then you have a smoothed image at this point. Okay, and if you subtract that smoothed image from the original image, you get a sharpened image, right, that we call as Laplacian, or edges, right. Then as I said, you already smooth the image, so no point in keeping a higher sampling rate, or it's okay to downsample now because you have condensed the frequency nicely. So you reduce the frequency nicely, so you can actually reduce the sample size also, right, because you don't need that much sampling now, right, according to the Nyquist criterion. You reduce the bandwidth, you can reduce the sample size. So that's exactly I am doing here. So I downsampled it, so image size is reduced, and again I applied the Gaussian filter, again I subtracted, I get the Laplacian of it, and again I can downsample, I can keep on doing this, right. So this filter, this if you see, this is known as the Gaussian pyramid, and this if you see is known as the Laplacian pyramid. Okay, so all I am doing is basically this sort of a mathematical operation. Okay, so it's something like let me call this guy over here as the Laplacian. Okay, and then this guy over here is the Gaussian. Okay, and this is my original image, so let me call it as I minus 1, right, because it's a previous stage. Okay, or maybe not, let me just call it as I only. Let's ignore this. Okay, so let me just erase it for you. Okay, so let me just remove that. So it's just the same scale, so that's why I call it as II. So what is II? So II is nothing but Li plus Gi, or rather other way, right. I think we defined Li in terms of this II original image minus smoothed version of this original image, and Gi is nothing but, always remember, it is a Gaussian convolved with your original image. Okay, so always remember that. Okay, so this is smoothing of the original image, I subtract the smoothed version from the original image, I get the Laplacian. So if I want to reconstruct the original image, all I need to do is you just put it back to the other side, and that's what exactly this. Okay, so this is Li. Okay, so Li plus Gi. Okay, so one thing you have to be careful, you are smoothing the image, so you're essentially losing some part of your image, so you may not be able to. So what I am saying is this II is nearly equal to Li plus Gi. Exact may not be possible because you are smoothing, right. This guy is smoothed version of II, so you may not be able to get the exact version, but for eye perceiving thing it looks almost same. Okay, and the same is applicable. So after that you are downsampling, right. So maybe you may want to call the next level. Okay, so I plus 1 is actually I. Okay, so this is downsampled by 2, let's say. Okay, so that means the image resolution, image scale is reduced by 2. Okay, so this is important because this is a very important operation, that's why you are able to scale the image, right. You are scaling the image further down, so this process keeps on repeating. Okay, so and then you can always, so given the Laplacian pyramid, you can always, so if you are given the Laplacian pyramid, right, you can always actually, so this is the lowest end of this, right, I mean lowest end of this basically what you call the last scale of the Laplacian pyramid. You're basically adding that to the Gaussian, you get the original image back, right. So that's sort of what you essentially do if you want to reconstruct the image back. Okay, so I will illustrate that using the code, then it becomes clear to you. So the same formula, what I'm saying is this. Okay, so you just can reconstruct the image always back. So that's the beauty. We didn't discuss that in the lecture last week. So we only discussed about the decomposition part, the scaling part, but it is always possible to reconstruct the original image back. We can always come back to this given this and this, right. So always, I mean this and this guy over here. So if we have these two guys, then we can always come back. Or let me just draw it again. This guy and this guy, if we have, we can always reconstruct this path back and come back to this original image. Okay, so that's very important to notice, because that's very important when we talk about the image blending part. Now, having understood this, now let's actually go back and understand what exactly happens in image pyramid. Okay, so what we are going to do is we are going to have create a Laplacian pyramid for this image and this image. Okay, so that is Laplacian pyramid for both image A and image B. So that's what you are going to do. The first step is that. Okay, so moment you do that, and then what you are going to do is basically you create a Gaussian pyramid of this guy. Always remember that. Always remember to that concept that we discussed. We want to remove that artifact which is coming at the boundary, at the seam. And what we did actually is we smooth the mask. Okay, so that's why exactly what we are doing here. We are going to have a Gaussian pyramid for the mask. The reason why no Laplacian here, because the mask has to be smoothed. Okay, so mask has to be smooth. So that's why we are going for a Gaussian pyramid for the mask. But we are going for the details of image A and image B. That's why we created the Laplacian for this. Okay, always remember the Laplacian inherently has Gaussian there. Okay, so always remember that. So if you have doubt here, when we create the Laplacian, we already have the Gaussian guy here, right? And similarly here, and similarly here. So when we say Laplacian pyramid, Gaussian pyramid is already inherent or implicit in it, right? We no need to explicitly mention. But when we say Gaussian pyramid, what essentially I have is you are not going to do the subtraction operation. Okay, so you will not have the subtraction operation. You only do sort of, you smooth the image, downsample it, you smooth the image, you downsample it. That's what the Gaussian pyramid is all about, right? You don't have the subtraction part. So for the mask I am going to do only Gaussian pyramid. For the image I am going to create the Laplacian pyramid. Okay, the fundamental reason for this is I am going to smooth the mask. And you can always remember that as I go down the scale, the smoothing is more and more, right? Because you are going to apply smoothing on top of it. So if you go back again here, so already you Gaussian filtered, you Gaussian filtered, you Gaussian filtered. So the image over here is 3 times Gaussian filtered. So it is more smoother. As we go down the pyramid, it is more smoother. And that is very interesting concept, because that's what we are going. If we have Gaussian pyramid of this mask, the last scale will have the most smooth version of it, right? So that's very important. And then this is the crux. The algorithm is so simple. Okay, so the concept is again same. This is the mask, this is that 1 minus mask, right? So that part is very clever, clear here. But instead of the image, we are going to apply that to each scale of the Laplacian pyramid. Okay, so this is the beauty about this concept. Okay, so Gaussian pyramid, 1 minus Gaussian pyramid, that is exactly remain the same. So basically you are going to create a pyramid. Okay, so you basically split this image into its pyramid, you split this also into its pyramid, you smooth this guy into its pyramid. That's why the Gaussian pyramid. Now each scale of the Laplacian pyramid of image A and image B, I am going to use the corresponding Gaussian pyramid mask. Okay, so that's what exactly does it. So this blend pyramid here is again a pyramid. Okay, it's not an image yet. Okay, so this is a pyramid. So each level I am going to actually do sort of blending, right? So each level I am going to do a blending, and I have created a mask pyramid also for that. And once you have this pyramid, you reconstruct it back, just like the idea that I was showing you. You add these two guys and then come back, you create the original image back. So if you do that, okay, you get a blended version, something like this. Okay, so that looks much better than the version that is seen over here. If you zoom in and see, you will see that this version will be much. I will have another example when I show you the hands-on. So that part makes it very clear that this is a really interesting approach. So what is the physical intuition happening here? And this is exactly mentioned in this line. The overall effect is to smooth the low spatial frequencies at lot, okay, at the seam, but to smooth high spatial frequencies only a little. It's a clever, I think it's a very clever idea, because what you are essentially doing is, as I said, as you go down the Gaussian pyramid, the mask will be smoother, right? The transition will be smoother more and more. Okay, and as you are at a higher level, it preserves almost the same shape. So that's exactly what I was telling in this expression, okay, or this line. Okay, so low spatial frequencies, that means you are at a lower level, lower scale, they are smoothed a lot. But high spatial frequencies, which are more at the top of the pyramid, they are really not that smooth. And if you do that, you will end up in getting a much better blending or much better composting, right? And it's very, very easy to do that. And let me actually pictorially represent this for you so that you get a better picture, right? Okay, let me do that for you. Okay, I just created sort of a pictorial representation for you here. So image A, you are going to have a pyramid of it. So this is Laplacian, always remember that. So this is Laplacian pyramid here. Image B also you have a Laplacian pyramid, and then mask you have a Gaussian pyramid, okay? And then what we are going to essentially do is each level, okay, each level, so this is a mask, so GMI is the Gaussian mask at ith level. So you're going to multiply that with the Laplacian of image 1 at the ith level, okay? So you multiply that, then you actually do the inverted one, so 1 minus GMI inverted mask here, and then corresponding level of the image 2, okay? So that's what is exactly happened. So equation almost remains same, but you're going to do it for this level, this level, this level, and then II is actually a pyramid again. So II is the pyramid image at this level, then this level, this level, and this level, and then once you are done that, you actually reconstruct the image back, okay? So that's a important aspect you have to remember. You just add up all the images to reconstruct the original image back, okay? So that's very important concept. So all you need to actually do is 3 simple steps. You create the Laplacian pyramid of A, Laplacian pyramid of B, Gaussian pyramid of mask. The moment you've done that, you use this equation to create the composting or the image, the final image pyramid, and then you do the expansion, basically reconstruction back to arrive at the final reconstructed image, okay? So hope it is pretty clear to you, and I would like to actually demo this to make it more clearer, and then it should be very, very thorough for you, okay? So let me just quickly show you the demo part. Okay, so this is a MATLAB code I just made for you, so it should be quite easy to follow. So we will read 2 images, okay, one apple and orange as we saw in the slide, and then of course I'm just resizing both images to the same size to make sure that there's no size issues. And then here I'm giving you a freehand option where you can draw the region to create a mask, okay? So it's quite straightforward. Since it's a color image, we have to repeat it over the 3 channels, okay? And then direct blend is nothing but you multiply, right? I mean basically mask into image A plus 1 minus mask into image B. So it's quite straightforward. And then what we do is we create the Laplacian pyramid for A and B and Gaussian pyramid for the mask. So I developed a function, basically borrowed from the file exchange, a function for creating the Gaussian pyramid, and it's quite straightforward. Let me just show you that also, how to create a Gaussian pyramid, okay? So we define the level, okay? So depth is basically some formula here to just to ensure that you go to some number of levels, okay? So based on the size of the image, okay? So you define some lower bound on the number of levels that you want to go down, reduce the scale of the image. Once you decide that and the mask or whatever, image or mask, whatever, and the number of levels you want to create the Gaussian pyramid is the input to this. And let's go to the Gaussian pyramid and see. So you basically go through each and every level, and then you basically need to subsample the image, that's all. So subsample is nothing but smoothing, downsampling. So I created a reduce function also. If you go inside that, it is nothing but a Gaussian kernel is defined, filtering is done, smoothing is done, and then basically I just downsample by 2, that's all, okay? So I fixed the downsampling factor by 2 here. And one important thing, very, very important thing for those signal processing people, they can understand it perfect, but even otherwise also, always ensure that when you downsample by 2, you have to ensure that your frequency content is also reduced to half, okay? So that's why that Nyquist criterion is important. You go back to the aliasing lecture and understand it better. But let's if you ensure this very heavy smoothing, then you don't have to really worry, okay? So I created a very heavy Gaussian filter here because the standard deviation is 1. So it's a very heavy Gaussian filter, but the downside here is you may remove a lot of details in the image, okay? So that's very important to notice. So essentially what we are doing in this reduce function is smooth the image, downsample the image, okay? So that's how you create the Gaussian pyramid, okay? So you first you have the image. So initially the subsample is nothing but the original image itself, and then what you do is you smooth that image, reduce the sample size, and that is stored here, and then you just keep on repeating till the number of levels. So Gaussian pyramid is nothing but you smooth the image, downsample the image, and you create it. Okay, so that's what we are doing. So we created the Gaussian pyramid for the mask and both the images. Okay, now for images, as we discussed, we need to create the Laplacian pyramid also, right? Because we are worried only about the Laplacian pyramid. Laplacian has the edges, right? Edge details. So to the Laplacian pyramid, what how are you creating Laplacian pyramid is from the Gaussian pyramid, right? Always go back to the formula here, right? You have the Gaussian pyramid, and from that you can basically create the Laplacian pyramid. Okay, so you're going to give the Gaussian pyramid. Always remember one thing: the first level of Gaussian pyramid is nothing but the original image itself. So if you go back here, you can see here the subsample you are initializing with image. Okay, and that's very important to actually notice. So the first level is sort of original image itself. Okay, and then what is inside the Laplacian pyramid? Let's actually open it and see. Okay, so this is the Laplacian pyramid. So if you see over here, okay, so I think the crux is basically this. Okay, so you Gaussian pyramid of I minus the temp. Temp is basically nothing but okay, so this function is also important. What is expansion? Let me just see that. Okay, so what we're doing over here is you pass an image and you're going to upsample it by 2, basically increase the size by 2. Okay, so that's exactly, so you initialize a zero matrix by twice the number of rows and columns of the original image. Okay, so you can ignore all this, actually it's not needed. Just delete it and make it simple. Okay, so just make it simple, and then what we are going to do is every second sample I am going to initialize with the image. You will have some zero samples in between, zero intensities in between, right? Because your image size is doubled. And then moment you have this image, what you need to do is the reverse operation. So you again smooth that image, that is like interpolation. So this is something like, because you have at this stage you have so many zero intensities, right? Because you are going to initialize a zero matrix, some of them is filled with the image, remaining is zero. So to have an interpolation, I am going to prefer a low pass filter here. So that's what exactly I am doing it here, and then scaling it because the intensity has to be averaged out, right? So you have to actually do sort of your your sample size is increased by 2, so I'm going to scale it by 4. Okay, so this factor is a factor dependent on how much size is increased for your image. Okay, so this process is just the opposite of the reduction. So here what we are going to do is you increase the size of the image by twice. Okay, exact opposite of that. So that's what exactly doing over here in the Laplacian pyramid. Let me just go back here. So this expanded image, the temp image, is nothing but equivalent to the original image. Okay, so the before smoothing operation, you can think about that. And then what I'm going to do is I'm going to subtract. Okay, so this is important, right? I'm going to subtract that smoothed image. This is the smoothed image equivalent from the original image equivalent, and then I get sort of Laplacian. So this is nothing but your Laplacian pyramid. Okay, as simple as that. So basically this operation, I think if you're confused, basically this operation is what we are going to do. Okay, so not this one, this particular operation. Okay, so it's hopefully it's very clear. So from the Gaussian pyramid I created the Laplacian pyramid. Okay, and then what we need to, so we have the Laplacian pyramid now, and now each level I go through each and every level, I create sort of this expression, right? I think let me just go back here. This particular expression is what we are essentially doing over here. Okay, so this is a blended pyramid I am going to create, and this is the Gaussian mask pyramid. Okay, the corresponding value at a particular level, and this is a Laplacian of A, this is a Laplacian of B. So basically the expression what is there in the slide. And once you have the blended pyramid, I just need to reconstruct the image back, and that is done using the expand operation. Okay, so just the reconstruction operation, and that's it. So once you have that, you have the final image ready, and then you can display it. Okay, let me just quickly run it for you. Okay, so this is the image. So I can choose the any mask for you. So some irregular shape I would like to choose. Okay, so it creates the this one. Let me just show you that. Sorry, there was an error actually. I need to rerun the code because of a small mismatch. Okay, so I'll just redo it for you. So I just select some random region for you. Okay. Uh, okay, so let me just open up one by one for you. So this is the original image. Okay, so this is the original image. This is the second image. Okay, this is the mask we created. Okay, so basically this is ready now. So if it's direct blend, basically I need to multiply this image by this image and then 1 minus of this image by this image and then sum it up. Okay, so if I do that direct blending, if I do, it looks like this. Okay, so this is direct blending and you can obviously see that seam is not perfect. And if I do the Laplacian pyramid way, you will get something like this. Okay, so you just compare. Okay, so this is after Laplacian blending and you see how beautifully it blended. Okay, so this is really interesting. Okay, and you could actually manually try smoothing this mask. Okay, so you just smooth this mask and then plug into this expression. That is what we discussed in this slide. Okay, so this operation, that also you can compare with the Laplacian blending and you will realize that Laplacian blending gives you some extraordinary result. Okay, and it's really very simple approach, but it's very powerful approach. Okay, so now let me show you another example. So this is more interesting. Okay, more practical case. So I'll have a cat image which is, the cat is actually lying in a, I mean, let me show you so that it will be much easier. Okay, so this is a cat image and it is actually lying in a grass and I want to put it across to another image which is fully grass. Okay, so I really want to take this cat alone and put it into a grass image alone. So let me just carefully draw the boundary of the cat. Okay, not really perfect. Okay, so let's finish it off. Okay, so that's it. So I chosen that. Okay, so let me actually show you what it looked like. Okay, so this is the first image, the increase to 1024. Okay, so the resolution is increased. Let me close this. You don't need this now. And this is the image I want to blend this. So I want to put this cat into this image. Okay, so you can see where I'm going. It's really the boundary looks similar, but I want to put this cat guy into this. Okay, so if I do direct blending, it looks like this. Okay, so this is the direct blending, simply placing the two together, and it looks good actually. I mean, if you carefully look, you can see the boundary is not really smooth. And now let me see how our blending, Laplacian blending looks like. And wow, you see here, this is just amazing, right? I mean, it doesn't look like this came out of something else. It's so beautifully blended, right? And this is why it's so powerful. And now you could actually argue with me. I think maybe I'll just zoom in and see you. This regions, right? Some region you can see the grass itself is different, and there is actually some ambiguity there. So this is not the perfect approach, but this works almost all the time. And this is one beautiful application of the Laplacian pyramids. And I would like to actually take you to another advanced stuff. Okay, so we won't discuss this, but there is more advanced stuff of blending, image blending, and this is one classic paper. So you can actually see it from this link, and a lot of MATLAB or Python implementations of this paper are available for you. So here what actually they are doing is slightly more. So it's a Poisson approach. So what they are actually trying to do is within the region, okay, within the mask, they will try to minimize the gradient between the source and the target image. Okay, so whatever there is differencing, okay, within that mask, they try to minimize, and along the mask or along the boundary, they want to keep the source image as close to the target image. Okay, as it is, not the gradient. Basically, this operation. Okay, so I mean within the omega. Okay, so within the omega, they want to keep the gradient, okay, as same, and outside it you want to keep it the image itself is basically the delta f or the gradient is 0 on the boundary. Okay, so it's slightly advanced, but it's quite easy to follow and very easy to implement also. This is not very difficult, and you can they have shown a lot of examples in this paper, which is slightly advanced stuff, and please go ahead and do this stuff for yourself. Okay, so with that I would like to stop the image blending part, and I will upload the code for you to experiment with. Just play with it, and left and right, if you have any questions, always feel free to come back to me. Okay, and next lecture we will discuss on the image compression aspect. Okay, thanks for listening, and see you in the next lecture.